This is a stoichiometry problem about the explosion of nitroglycerin. When nitroglycerin explodes, it does so according to the equation shown here, where the products are carbon dioxide, nitrogen, water, and oxygen. You can see the stoichiometric ratio. For every 4 moles of nitroglycerin, you get 12 moles of carbon dioxide, 6 moles of nitrogen, 10 moles of water, and 1 mole of oxygen. So in order to figure out the volume of each product formed when 100 grams of nitroglycerin explodes, we need to figure out how many moles of nitroglycerin we have, and then therefore how many moles of each of the products. Now this problem is done at standard temperature and pressure, or STP. So remember that that means that the temperature is 273.15 Kelvin and the pressure is 1 bar. So the first thing we need to do is figure out how many moles of nitroglycerin we have. Well, if we have 100.0 grams of nitroglycerin, and the molar mass of nitroglycerin, which you can look up, add the components together, is 227.09 grams per mole, that tells us that we have 0.44035 moles of nitroglycerin. So if we have that many moles of nitroglycerin, then we can apply the stoichiometric ratio for each of the products to determine how many moles of each of the products we have. So for example, 0.44035 moles of nitro, I'll write nitro for nitroglycerin, and I know that there are 4 moles of nitro for every 12 moles of CO2. Right, that comes from this stoichiometric ratio. That tells me that I'm going to have 1.32 moles of CO2. So let's put that up here, 1.32 moles of CO2. I can use the same approach, taking the number of moles of nitroglycerin and the appropriate stoichiometric ratio for each of the 3 other products. So this would be 6:4 if it's nitrogen, it would be 10:4 if it's water, and it would be 1:4 if it was oxygen. So by doing that, I can calculate the number of moles of each of those other 3 products, and I get 0.6605 moles of nitrogen, 1.100 moles of water, and 0.1101 moles of oxygen. All right, so now I have the number of moles of each of the products formed, but what I want is the volume. So that requires me to look at the ideal gas law, PV equals nRT. I want to calculate the volume, so by rearranging this equation, or dividing through both sides by the pressure, I get that the volume is equal to the number of moles of the gas in question times the ideal gas law constant in the appropriate units, and then the standard temperature divided by the standard pressure. So for instance, for the volume of CO2, I would put in here 1.32 moles. I'd use the gas constant 0.08314 because that has units of liter bar per K mole, and then my temperature is 273.15 Kelvin, and that whole thing is divided by 1 bar. So now if you look at the units, moles cancel, Kelvin cancels, bar cancels, leaving us with units of liters, which is what we'd expect for volume. And if I do the calculation here, I get 29.98 liters of CO2. All right, I can do the same thing for the other 3 reactants. All I have to change is the number of moles that I put in here, right? Because a mole of ideal gas carbon dioxide versus ideal gas nitrogen, etc., doesn't make any difference. So I substitute in the values that I calculated above for the number of moles of each of these gases and do the same calculation. And if I do that, I get that the pressure, or the volume of nitrogen is 14.998 liters, the volume of water is 24.981 liters, and the volume of oxygen is 2.500 liters. So how many significant figures should I have here? Well, I'm given 4 significant figures in the mass of nitroglycerin, and the only other number I used here that's not a whole number from the stoichiometry is the molar mass. I have 5 significant figures listed there, and then of course in these stoichiometric ratios we consider those to be exact numbers. So these answers should be written in 4 significant figures. So the carbon dioxide one is fine, the nitrogen one should be 15.00, the oxygen or the water one should be 24.98 liters, and then the oxygen one is 25.00 liters. Okay, we can further. Here's a variation on this problem. We take this same 100 grams of nitroglycerin and let it explode in an otherwise empty 50-liter gas cylinder, and the pressure or the temperature stabilizes to 220 degrees C. So now we have a situation where the volume is specified by the gas cylinder size and the temperature is not standard temperature. So we want to figure out what the overall pressure in the cylinder will be under these circumstances. So again, the ideal gas law, PV equals nRT, I can rearrange it, solving this time for pressure instead of volume. And this is the equation that I come up with. I'm given the temperature, I'm given the volume. What do I put in here for the number of moles? Well, I want the total pressure, right? So this is going to be, the number of moles will be the total number of moles. And on the previous slide, we looked at calculating the individual number of moles of each of the products. And if we add those all up, we get that there's a total of 3.1901 moles if you add up the carbon dioxide, nitrogen, water, and oxygen. So that would be the number that I'd put in here for N. The temperature is 220.0 degrees C, but I need it in Kelvin, so I add in the conversion factor, giving me a total temperature of 493.15 Kelvin. So substituting these into the equation, 3.1901 moles, the gas constant in the appropriate units, and then the temperature, 493.15 Kelvin, all divided by the volume, 50.0 liters. If I do that calculation, I get 2.6159 bar. How many significant figures should I have here? Well, based on the previous slide, I should have 4 in my number of moles. I should have 4 in my temperature, but I only have 3 in my volume. So this should be answered as 2.62 bar, and that's the total pressure in this container. The next problem is to look at what is the partial pressure of each of the gases in the product mixture when this same 100 grams of nitroglycerin is exploded in this 50 milliliter container or 50 liter container. Partial pressures are given by the mole fraction of that particular chemical species times the total pressure. So we would write, for instance, the partial pressure of CO2 would be the number of moles of CO2 divided by the number of moles total times the total pressure. On the previous slide, we calculated the total pressure, 2.62 bar, and we also noted what the total number of moles, 3.19 moles. And we know what the number of moles of CO2 are from the previous slide, or 2 slides ago. So we can just add these put these numbers in here. So we've got 1.32 moles of CO2, 3.1901 2.01 moles total and 2.62 bar as the total pressure. Doing that calculation, I get the partial pressure of CO2 is 1.083 bar. Now, for the other three products, nitrogen, water, and oxygen, all I have to change here in this calculation is the number of moles of the chemical species in question. So if I do that, I get the partial pressure of nitrogen. There I would divide by 0.6605 moles, or multiply by 0.6605 moles. I get a partial pressure of 0.5415 bar. The partial pressure of water, I get 0.9020 bar. And the partial pressure of oxygen, I get 0.0903 bar. Now these should all be listed according to 3 significant figures because I'm limited by the number of significant figures in my total pressure. So this should be 1.08 bar for CO2, 0.542 bar for nitrogen, 0.902 bar for water, and 0.0903 bar for oxygen. And if you add those all up, you should come up with the same total pressure, 2.26 or 2.62 bar, the total pressure for the whole mixture, because these are the 4 things that are there.